Hey, Honors Pre-Calc. Today we're going to be learning lesson 8.3, techniques for evaluating limits. The essential question is, how are common techniques of evaluating limits used to solve limits? Here's what we are going to do. You're going to be able to recognize when a limit statement is in indeterminate form. And indeterminate form means that our direct substitution method of evaluating a limit that we learned last lesson won't work. So unfortunately, that means we have a little bit more work to do, and we will learn how to use the dividing out and the rationalizing techniques to solve limits in indeterminate form. So we're going to learn two different methods to solve limits today. You already know about the idea of a conjugate pair, rationalization, like if a square root is in the denominator, and the idea of common factors that'll come up today. And here's an example of a limit that we'll be able to solve. So just to give you a preview, we're going to look for a way to factor the numerator here so that we can find a common factor to cancel. So with that being said, let's head over to the notes. All right, here we go. 8.3, techniques for evaluating limits. First of all, we have to know what indeterminate form means. If you try to use direct substitution and you get a fraction 0/0 as the answer, this value has no meaning as a real number, and we must use a table, a graph, or one of these following techniques, which are specifically more precise and more accurate in order to solve. A table and a graph, like we learned in the first lesson of this unit, are really approximating limits. Dividing out and rationalizing are going to give you precise, exact answers. So that's what we want. So let's take a look at letter A. In letter A of example 1, if we try to plug in -3 right now into this fraction, what happens? Let's check. We end up with 9 minus 3 minus 6. So 0 on top, and -3 plus 3, 0 on the bottom. 0/0 means that this is in indeterminate form. We can't use direct substitution because it doesn't give us a valid answer. Specifically, what's probably happening here is that we have some sort of a graph that has a hole in it, like this at our point. So if we're trying to plug in -3, there's a hole there, so we're not actually getting a value, but the graph can still approach the same number from each side. There's mathematical algebraic ways that we can figure out what that hole is by removing it. So what we're going to be doing here is trying to factor the numerator. We still write the limit statement in front. And on top, we try to see, okay, what can this factor into? It can become x plus 3 and x minus 2. And now you can see that we have a common factor on the top and on the bottom, the x plus 3. So I'm going to cancel those out, which in a normal fraction we want to be careful about because now we're canceling out x's, which really changes the function. But since we're inside of a limit, we're allowed to do that, and it doesn't change the value of the limit. This is still equal. I can still write this equals sign here, even though I'm canceling out the x plus 3's. That's a special property of limits. And what we just did there is because we canceled out the same factor on top and the bottom, we removed the hole. So it's as if we came back up to this line and just drew a line straight through, ignoring the hole. Now we filled in the hole, so we can plug in -3 for x, just like normal direct substitution, and get the real answer. So we have -3 minus 2, which is -5. All right, so that's what we're going to do for letters B, C, and D. So let's try letter B. If we try to factor this one, well, first, if we just try plugging in -1, we're going to get 0/0. So we're going to have to factor. I end up with x plus 1, x minus 3 on top, and x plus 1 on the bottom. And the x plus 1's cancel and just leave me with the limit as x approaches -1 of x minus 3. And now we can use direct substitution, -1 minus 3, so we get -4. All right, two more. The next two have interesting factoring techniques. In letter C, we have a 4-part polynomial, 4-term polynomial that we have to try to factor. So this equals the limit as x approaches 1 of x minus 1 over x minus 1 times x squared plus 1. Now, if you weren't sure about that, I can understand that. We're not really used to factoring quadrinomials, potentially, but that you can technically use the box method for most of these. If we fill in one by one each of these terms into this box here, and then try to pull out on top and to the side, like a reverse Punnett square, we can pull out the common factors. So x cubed and x have an x in common. Negative x squared and negative 1 have at most a negative 1 in common. X cubed and a negative x squared have an x squared in common. X and a negative 1 don't have anything in common, so it's just 1. And as long as we can kind of move forward through the Punnett square, multiply what's on the top and on the left, and get what's in the box, then we're good. So x times x squared is x cubed. X squared times negative 1 is negative x squared. X times 1 is x. Negative 1 times 1 is negative 1. So we got x minus 1 as our first factor, and x squared plus 1 as our second factor. I can write a little plus here. So that's one method to do that if you didn't know how. So that could work. But let's keep going. So now that x minus 1s can cancel, we're left with the limit as x approaches 1 of 1 over x squared plus 1. Now we can plug in 1 successfully, and we get 1/2. Let's try letter D. This time we have a difference of cubes. So let's just remember this formula, as I believe you learned these in Algebra 2. We have sum of cubes and a difference of cubes. And what you need to remember is that there's an AB factor and an A squared AB B squared factor. And then we use SOAP to fill in the blanks. The first operation is always the same as the original. The second one is always opposite. And the third one is always positive. So SOAP, same, opposite, always positive. So same, opposite, always positive. So that's how we remember those formulas. So this is a difference of cubes, so it's going to be the second one. A is going to be x, and B is going to be 2, because 2 cubed is 8, and x cubed is x cubed. So we're going to end up with the limit as x approaches 2 of x minus 2, x squared plus 2x plus 4 over x minus 2. And the x minus 2's cancel out, so we just get the limit as x approaches 2 of x squared plus 2x plus 4. Now we can plug in 2, so we get 2 squared plus 2 times 2 plus 4, or 4 plus 4 plus 4, so we get 12. All right, so that is the dividing out technique. There's one more technique we're going to talk about, which is the rationalizing technique. On the back, example 2. So we have, for letter A, the limit as x approaches 0 of the square root of x plus 1 minus 1 all over x. If we plug in 0 right now, we would end up with the square root of 1, which is 1 minus 1. So the top is 0 and the bottom is 0. Ding, ding, ding. We have indeterminate form, but this time, since we have a square root involved, there's no way we can factor the top to cancel out any x's or anything like that. So instead, we are going to rationalize by multiplying by a conjugate pair. So whichever part, either the numerator or the denominator, wherever the square root is, we're just going to take that square root, and if there's an operation between the square root and another number, we're going to switch it. So we're going to multiply this by square root of x plus 1 plus 1 over the square root of x plus 1 plus 1. So we're not changing the value of the fraction. We're just multiplying by the same thing on the top and on the bottom, which is technically equal to 1, because we're multiplying by something divided by itself. So we're multiplying by 1. That doesn't change the value of the fraction. It just manipulates it. So that's what we're dealing with here. I am going to distribute the numerator and keep the denominator factored. We have to write limit every step of the way, though. So on top, now we have to FOIL. So we have square root of x plus 1 times the square root of x plus 1, which is going to give us x plus 1. We have the square root of x plus 1 times 1 -1 times the square root of x plus 1. And then -1 times +1. And I'm going to leave the bottom factored. And now on top, a lot of nice things are going to happen. The square roots cancel and the +1 -1 cancel. So we just get limit as x approaches 0 of x over x times the square root of x plus 1 plus 1. And now you can see why we left the bottom factored, because the x is canceled. So we get the limit as x approaches 0 of 1 over the square root of x plus 1 plus 1. And now we can successfully plug in 0 for x. And we end up with 1 over the square root of 1, which is 1 plus 1. So 1/2. All right. So once we successfully cancel things after we rationalize and multiply by conjugate pairs, then we can usually plug in the value using direct substitution and solve like normal. So let's try letter B. Same idea. Square root of 2x plus 1 minus 1. The conjugate pair is going to be the square root of 2x plus 1 plus 1. So we end up with, on top, after we FOIL, 2x plus 1. Now this time, since we've already done this once, I can tell you that when we multiply conjugate pairs together, the outer and the inner always cancel out. So we're just left with the last part, -1, over x times the square root of 2x plus 1 plus 1. The +1 -1 cancels, so we're left with the limit as x approaches 0 of 2x over x times the square root of 2x plus 1 plus 1. The x is canceled, but the 2 stays. So we get the limit as x approaches 0 of 2 over square root of 2x plus 1 plus 1. Now we can plug in 0. We end up with 2 over 2 times 0. So 0 plus 1 is 1. Square root of 1 is 1. 2 over 2, which is 1. So there you have it. That is the rationalizing technique. Now you know 2 different techniques to solve limits when they are in indeterminate form. Hopefully that makes sense. Please let me know if you have questions, like always, and I hope you have a great day. Thanks for watching.